Okay, so today we're going to introduce this new idea that we really haven't talked much about. We've talked a bit about electrochemistry and being able to identify oxidation and reduction. We've talked a little bit about calculating cell potentials. But the next thing I want to introduce here is how cell potential is related to work. Okay, so electrical work. When we think about electrical work, what we really want to understand is that, remember, work is a force times a distance when we do apply a force times a distance on something. But the work that we're doing here, it's electrical work because we're really causing electrons to move. Right, that's the work we're talking about. A bunch of electrons are going to be moving. And now we can utilize that work. We can utilize the movement of electrons to do things. Right, and that's how we power various electrical devices. We use the work that's being done on electrons to do stuff. Right, it's that energy that we're dealing with in terms of work. Now, the electromotive force, or the cell potential that we're talking about, is measured in volts, which is work in joules, right, over the charge. Okay, so this potential, the potential difference is going to be how much work can you do given a certain amount of charge moves from one place to another. So if we think about the potentials and how we have a potential for a given redox reaction, right? Let's say we can think about the redox reaction whereby you have 2H plus. Actually, let's not look at that one. We'll use a different one. Let's go with zinc, right? So zinc 2 plus 2 electrons reacts to form zinc solid. Okay, that has a potential E naught of the half reaction of negative 0.76 volts. Now, no matter how, like when you combine two reactions, it doesn't matter how many of these reactions you have, it's always going to have this same cell potential. Because if you look at the charge that we're dealing with, or excuse me, if you look at the units we're dealing with, is that potential, that half cell potential is in terms of volts, which is the work that you do per unit charge. And the charge that we're talking about is the charge of moving, coming from moving those electrons. And so it's per, that work that you can do per 2 electrons, essentially, in this particular half reaction. Whether you double the half reaction or triple the half reaction, yeah, you're going to triple the work or double the work, but you're also doubling the electrons, so the potential stays the same. And so that's a key thing here, right? We don't do anything to those half cell potentials when we add them together. Even if we take 2 of one half reaction and 1 of another one, we don't do anything with those. We just take the half cell potential at the cathode minus the half cell potential at the anode, and just do that. It's as simple as that. You never have to multiply those by 2 or 3 or whatever, right? There's no multiplier. So when we think about now, so that's one of the things I wanted to bring up there. Another thing is when we think about the work, right, that we're doing, right, the work that's being done on those electrons, okay, that's what we have up here, right, this work over charge, okay, so the work over the charge. And so what we can do here is say, okay, if we think about the charge as being the total charge in coulombs, right, and so if that Q is the positive charge, and the cell, for a positive cell potential, the reaction is doing work on the surroundings, that must mean that if we have a positive cell potential, right, so if E of the cell is positive, we're going to be doing work on the surroundings, which means that the work for the system, so I can put SYS there, right? If we're doing work on the system, or we're talking about the work associated with the system, the work associated with the system is going to be the negative of the charge times the total charge that you have times the potential of that system, okay? And so what we can think about now is that W, that work, that's the maximum amount of work that can be done. Essentially, when we say the maximum amount of work, we can assume that all of the energy, right, that all of the potential right, goes to moving electrons, right, which would be the kinetic energy of moving those electrons. And none, right, none goes to the heat. Now, that's not a great assumption, but that's something that we can think about when it comes to, say, moving electrons through wires, because the amount of heat is relatively small compared to the work that you're doing when you're moving the electrons. And depending upon the actual system that you have and the wire that it's going through, the resistance and that and whatnot. So we're kind of assuming that there's no resistance. We're moving all of these electrons, and none of that movement, none of the energy that's being used here is going to heat up the wire. So in that case, we have that W will often be written as W max. Okay, so the maximum amount of work that you can do on those electrons. And so something else that we know is that, well, since the energy of a reaction is the heat, right, plus the work, or the change in energy of something is the heat plus the work, or the change in energy is associated with the free energy, well, then we can say, well, if the heat is 0, right, then the maximum amount of work we can have a system do, or that can be done on a system, is going to equal the energy, the free energy of that thing. So now we can plug the delta G in for our W max that we had from this equation here. And we can say, okay, so that's negative Q times E. But we can also change that, because we know that Q is related to charge, okay? And charge, so Q is going to equal N times Faraday's constant, where N is the moles of electrons and F is Faraday's constant, right? And Faraday's constant is actually really simple. Faraday's constant, as you can see here, this F has a value right here, right? And all that's just a relationship between the amount of electrical charge in terms of coulombs to the number of moles of electron. Remember, most of the time when we've done charges in the past, we've dealt with like +1 or +2, right? That was just based on the relative charge and the number of electrons. Here we're talking about the actual coulombic charge, which is the SI unit for charge. And so now you can relate the amount of free energy associated with a redox reaction to the amount of charge that moves and the cell potential. Okay. Of course, if you have that reaction is under standard conditions, that gives you delta G naught, right? So you can say that the free energy of a reaction occurring at standard conditions is related to negative Q still, right? That's still the charge. The charge doesn't matter whether it's standard conditions or not, but now it's going to be measured based on the E naught of the cell, okay? And so you can say, okay, well then it's N times Faraday's constant times the standard cell potential, okay? So taking that stuff, we can now derive another equation that relates the delta G, right, to the delta G, right, the reaction's spontaneity under any conditions to the reaction spontaneity under standard conditions. Now, something to remember that we've done in the past is we've done relationships where you had something like Q over K, or the natural log of Q over K, right? If Q over K is less than 1, the natural log of Q over K is less than 0, right? And you would have a delta G, which was less than 0, which would mean that was a spontaneous reaction in the forward direction. Here, though, since a positive value for the self-potential means that it's spontaneous in the forward direction, right? Then if you have a value that's greater than 0 for the self-potential, that's going to mean a spontaneous reaction. So we can now look at the magnitudes of all of these things and use any one of these things as a way of determining whether a reaction is going to be spontaneous in one direction or another, or non-spontaneous. And so what we're gonna do starting tomorrow is we're going to utilize this relationship whereby the free energy of a reaction is governed by the delta G naught, right? Or the free energy in this of the standard free energy of the reaction plus RT ln of Q. And all we can have to do is substitute in those values that we had 2 pages ago, right? For the for this particular for each of those values, right? The standard free energy of the reaction and the free energy of the reaction. And we can take that and use that to look at the cell potential. And we can use that if you just divide each of those by negative in F, right? Divide by negative in F, divide by negative in F, you get this equation here, which relates the cell potential to the standard cell potential minus this constant here, where n, again, n is the number of electrons still, but the rest of it is constant, and Q is just that reaction quotient, just like we've done in the past. And so what you can do now is say, well, okay, and at least what's been done in the past by convention is to switch this from, notice, from natural log to log, which is just a multiplier of 2.30, and then take RT, where T here, right, is considered to be at 298 K, right, or at 25 degrees Celsius. And the reason for that is most of these chemical reactions we're going to monitor are going to be at 298 Kelvin, or at standard temperature. And so generally we use this when we're looking at cell potential versus standard cell potential. And again, N is going to be the number of electrons in a given reaction. And so that would be governed by, for example, if you have the reaction we looked at before where we had copper 2 plus, right, plus zinc solid is the one we looked at yesterday, right? That reacted to form copper solid plus zinc 2 plus, right? This involves the transfer of 2 electrons, right? And those electrons, that 2 electrons, that's something that you can figure out just based on when you balance chemical reactions by their half reactions. That half reaction method is going to be the number of electrons there. So that would be essentially N here would be 2, right? N equals 2 there, right? So that's how you'd figure out the N value for any of these, right? And you can figure out your cell potential, just the potential, half cell potential at the cathode minus the half cell potential at the anode, plug in your value for N, solve for your solve the rest of it using the concentrations of your products and reactants in the reaction quotient. And that's what we're going to do tomorrow as we finish up chapter 18's material, and we'll start in on chapter 22 on Monday. Okay. And so with that, you'll see that the next thing we're going to get into is utilizing concentration to figure out standard cell potentials. So we'll stop there for the day and let you do some balancing, some redox reactions. So think about that as you're balancing redox reactions. Think about the number of electrons in the overall redox reaction.